So the last video ended with me talking about in general that if you have an equilibrium constant that it refers to the concentration of the products over the reactants raised to their coefficients. Okay, so now we're going to try an actual example with some numbers in it and see what happens. Okay, so lots of exponents, a little bit of algebra going to happen here. It's okay, we'll figure it out. So for this same reaction as we had talked about at the end of the last one, okay, we know that at equilibrium, the ratio of the products over the reactants is going to be 1.84 times 10 to the negative second. Because it can make that decimal a little more legible. So what we want to know is if you're at equilibrium and we know the concentration of this, which is H2, is 0.025 and the concentration of I2 is 0.035, well then what's this going to be? So this is what a reaction would look like on a quiz or exam. It doesn't have the generalized balanced equation. You need to know what it is. So the general form of this is that it's products over reactants in the concentrations of each raised to their coefficients. So there's no number in the front here, so there's no exponent here. Basically it's a 1. Okay, and they're multiplied together, divided by HI, and because there's a 2 in the front, this is squared. Well, now it's just algebra. We know this one, and KC was given, so we're solving for this one. So we're going to have to do some algebra to make that happen. So what we need is HI all by itself. So HI squared is in the bottom. I'm going to get it out of the bottom by multiplying both sides by HI squared. All right. I think my pen might be dying, but we'll figure it out. Okay. So that will cancel that out. And now it's on this side. Since we need HI by itself, we're going to have to get rid of KC. So if we divide KC off of both sides, these will cancel out. And then we'll be left, we're not done, but I'm going to rewrite it. We have on the left side, HI squared is equal to H2 times I2 divided by KC. Well, we need to get rid of this 2. Okay, so basically this is squared, and we want one of them, so we're going to have to take the square root of both sides. When you take the square root of both sides, we could do the little, like the thing that looks like the division symbol-ish thing, the square root symbol. We also could multiply, raise each side to the 1/2. I don't care which way you do it. For this one, I'm just going to write it like this because I'm lazy, but if you wanted to do all of it in parentheses, raised to the 1/2, it means the same thing. Okay, so I'm going to rewrite it just so that it's clear in your notes. This side is now equal to the square root of H2 times concentration of I2 divided by KC. We have all those numbers. Square root is a button on your calculator. We're just going to plug everything in. So the square root of H2 is 0.0250. The units don't really matter here. It's going to work out to be molarity because KC doesn't explicitly have units. Okay, and this value is 0.0350, and KC was given. It's 1.84 times 10 to the negative second. So, typing into your calculator. Okay, I'm actually going to divide all this stuff and then take the square root. So 0.025 times 0.035 divided by 1.84 e to the minus second. That's the stuff under the square root symbol. So now I'm going to, secondary function of the square is square root. Square of that answer, and I got an answer of 0.218. Okay, we saw in the last video that no matter what we started with, the reactants or products, no matter what, that when we got to equilibrium for this particular reaction, we ended up with significantly more of the reactants than the products. And you'll note that this is like about a factor of 10 more than 0.025 or 0.035 is this 0.2. So that seems about on par with the answers we were seeing for the examples that led to this reaction. Okay, so nothing too profound, nothing new really, but that's okay. All right, I do, before we get too far along here, want to talk about how this actually relates to kinetics. We had an entire chapter. Chapter 14 is about kinetics, rates of reactions. So we need to talk about how this actually works. Okay, so I'm going to keep using the same example. So we have a forward reaction and a reverse reaction. We write it as the reversible arrow. It's H2 and I2. For some reason, this textbook loves this example. Okay. So the way we can visualize this is we could keep track of this in terms of, we could visualize there is a forward reaction, and that's the rate constant for the forward reaction, for like the rate law constant. And then there is a reverse reaction, which I'm going to do in a different color. I am going to try to avoid talking about rate constants at the same time as equilibrium constants because they're both described as K, which is kind of a fundamental design flaw of this whole setup. But for right now, for this particular chunk, that's what we're going to do. So if we had this reaction, we could visualize this in terms of kinetics. So this is referred to as the kinetic view of equilibrium. We are not going to make a huge deal out of this, and honestly, for the most part, the previous explanation of equilibrium constants is more important than the kinetic view, but I do want you to understand that it is all connected. Okay, so if we assumed these are all elementary steps, so when we talked about mechanisms in the last chapter, we said that elementary steps, basically the coefficients become the exponents. And we're going to assume that here because it makes our lives easier. Otherwise, to get rate laws, we'd have to go through all the legwork to get rate laws for forward and reverse reactions. So essentially, the rate of the forward reaction would be equal to, I'm going to try to keep the colors consistent, would be equal to the rate constant of the forward direction times concentration of HI squared. We can square that because we're assuming it's an elementary reaction, so the coefficient in the front becomes the exponent. And the rate of the reverse reaction is equal to Kr, because it's the reverse, times the concentration of H2 times the concentration of I2. So I know that our rate laws were in terms of reactants, but if we were visualizing the reaction going this way, you could visualize these as reactants and this as products, which is why this still works that way. Okay. So the fundamental idea of equilibrium is that you reach equilibrium when the forward rate and the reverse rate are equal. So basically, at equilibrium, apparently I can't spell or write legibly, sorry about that. Basically, the forward rate, rate forward is going to be equal to the rate in the reverse direction. And that's how we know we've gotten to equilibrium. Well, because this is now equal to this, we can set these two things equal to each other. So I'm going to do that real fast. Switching colors is going to be a pain, but I'm trying to keep it consistent. Okay. So we said that there is a equilibrium constant for this. So Kc for this reaction is equal to the products over reactants, which is H2 times I2 divided by HI. We literally just did an example that has this stuff, squared. Okay, nothing surprising here. Well, if we wanted to rearrange this so that it's equal to this, we could divide this HI squared to the other side, so it'd be in the bottom, and we could divide Kr, and it actually comes out to be equal to the rate constant of the forward direction divided by the rate constant of the reverse direction. Okay, we don't typically use this interpretation. Usually if you've got this, we're ecstatic. I'm super happy that you can do that, but this understanding that this is how it works is somewhat important. Okay, all right, so big picture, the way Kc works, so switching topics a little bit here, is that it is products over reactants raised to their coefficients. So I'm going to just write the word coefficients. It's oversimplifying it, but the basic concept is there. So in terms of using this, you can actually just glance at a Kc value and know whether the products or reactants are more stable or which way the reaction is more likely to go. Okay, so if Kc is larger than 1, so suppose you had products and reactants, what this means is that the forward reaction is the dominant reaction. Means it's more likely to go forwards than backwards. It also, and that is partly because the products are more stable than the reactants. So the other way to interpret this is products are more stable than reactants. Okay. If Kc is less than 1, the opposite is true. The reverse reaction is dominant. And the reactants are more stable than the products. Kc can vary a lot. It can be anywhere from like 10 to the negative 15th all the way up to like 10 to the positive 15th. So if it's anywhere near 1, you basically assume that the products and reactants are, you know, about the same in terms of stability, and the forward and reverse are equally likely to occur. But you can have numbers of like, Kc could be like 1 billion. It could be 1 trillion, whatever. It could be a really huge number, which would mean that the reaction goes predominantly forward. Kc could also be like times, like, you know, a number times 10 to the negative 12th or something, which would mean that the reverse reaction is the main one. Okay, so you can actually just look at the Kc value and know which way this reaction is going to go. So, for example, this one that we started with, Kc is 10 to the negative 2nd. This means that the reaction, which is less than 1, means that the reverse reaction is more likely to happen, which means at equilibrium you should have more of this than this, and this is more stable than these, which is what we saw. We said when we got to equilibrium, these things, the HI was about a factor of 10 more than this, each of these individual ones, okay? So you can honestly just kind of glance at Kc and get at least a ballpark idea of which way things are going to shift and which is more stable reactants or products, okay? Kind of weird stuff. It's not too bad, but, you know, it's all right. All right, thanks.